Okay, hello everyone. I can tell from the sort of the fervor in the room that most of the homework assignment due soon. I also will say that there's been a couple of bugs that have come up with the auto lab assignments, and it's a learning experience for us too. I think what we've learned so far is we should never require you to use CVX opt or NumPy types or anything like types of these different arrays to return them. We should just use straight Python lists. So for this assignment, you have to deal with the conventions that we have in terms of what to return, what we're passing to you and what we're going to return. But for future assignments, we'll just convert all those to straight Python types. I think everyone will be happier if we do that, and it'll just be easier for everyone that way. But for now, we'll sort of keep with the current setup. Yes.
I think just the biggest thing would be is if the function prototypes that you give us, they can go just plain prototypes can go into AutoLab and get a 0, but actually.
I see. Okay. Yeah. All right. I think that might also. There were some issues with like some things would give you a type, would give you actually a good credit even if you said nothing or had like an empty array. So yeah, it's a good thing to try. Okay. The other thing is, I think we're actually just going to go ahead and say for the auto lab assignments, because of all these issues that are coming up, I mean, it's supposed to be after 2 weeks, so we're just getting up now. We'll go ahead and push the deadline for just those two parts back until Friday. So basically, you get some of your late days for free for those ones. Please don't use this as an excuse to put it off 2 more days before you start now. Like, still work as if you're doing this for tomorrow, for Wednesday. But just to avoid kind of the stress I know it will cause, we are getting this set up ourselves as well, so I think that's reasonable. Hopefully it's a good compromise, right? It's not the full 2 weeks they're gonna be open anymore, I guess, but it's a little bit more time. The 2 auto labs, so just the 2 programming parts. So the written assignment is still all due on class at the beginning of class on Wednesday. The programming assignments we will let you submit up until the start of class time, so 1:30 p.m. on Friday. So push it back 48 hours. I will post that on the message on the Piazza board, just to clarify that. But you get the privilege of if you're here in class now, you get the privilege of finding that out soon, I guess. Were there any other questions that came up though? I have office hours for after class today, so I will have them from 3 to 4. Vittorio had them early today. He has them again tomorrow. We'll have them again Wednesday after class, so hopefully there'll be enough office hours to get and then Thursday again, so actually have plenty more office hours to talk about these things. But do come to office hours. Are there any sort of questions that you think, though, that would be applicable to everyone? Most people are doing actually a very good job of asking those on the message board, so we can just keep doing that. But was there anyone that sort of had a very pressing concern about the homework? Okay, so then we'll just keep chatting in office hours then, as we have been, and go from there. But with a little bit extra leeway that you have 48 more hours for the programming parts. And we'll post a message to that effect on the board. Were there any other questions about either the topics from last time or... That's probably your main focus of the homework these days, so you're probably not too concerned about anything else right now. So, all right. Well, as I said, have a lot of office hours coming up. We're doing our best to try to fix the bugs as soon as they are mentioned, as they're pointed out to us. But more may come up, and then we'll deal with them as they come. So please do submit as if the deadline was Wednesday, but just know that you have a few more days. And then the next assignment is going to be out on Wednesday, as before. That won't be pushed back. And I think from now on, that we'll also try to make sure that we just use standard Python types for all the... You have to use internally CVXPy and all these kind of things, but we'll just use standard Python types for the input and output. Yeah? Sure, yeah. I think they'll make it easier if they are, in fact, standard Python types and not CVX opt variables, not NumPy variables. So I think that was a big issue. We were sort of saying that it's a matrix like this, but it could be one combination of the other. So yes, we'll just use specify the standard Python types in the future, and yes, maybe also have it so they return a 0 score by default. Okay, so having said all that, hopefully it's still enjoyable, even if there's some hang-ups. So, okay. Today we are going to start one of our 2 lectures in machine learning, and 2 lectures is pretty short amount of time to do all of machine learning. So we're not going to do all of machine learning, but we will do, hopefully get you some idea of what machine learning is, and really more than that, get actually some fairly sophisticated algorithms under your belt when it comes to machine learning. So the outline for these 2 lectures is going to be the following. It's going to give a brief introduction first, and then talk about regression. And regression is the case of predicting real valued outputs. So you've actually already seen regression before when I gave the very short example on least squares modeling. We're going to use different notation here, though. And machine learning as a whole has somewhat different notation from most optimization, even though machine learning uses optimization. So I'll define this a little bit more concretely in terms of both problems and in terms of the things you might want to solve given certain input and output data. Then I'm going to talk about nonlinear regression. And I'm putting nonlinear in quotes here because some people would call what I'm doing linear regression. It's just that we're using nonlinear features of data to capture nonlinear functions, but still using actually what's called a linear hypothesis class. And then we're going to talk about overfitting and model selection in those categories here. And that's actually going to be it for today. Those 3 things are going to be what we cover today. And the next time we'll talk about classification. Classification is when you want to predict discrete outputs. So if you have one number of choices you want to predict, that's classification. And then we'll talk about sort of a bunch of other machine learning algorithms. And what I mean by that is, in the time that we're talking about these things, regression and classification, by the nature of time, we are limited to talking about sort of a finite number of different machine learning algorithms. We're going to cover, in particular, linear regression. We're going to cover support vector regression, or something that goes by the name of support vector regression. It's kind of a simple algorithm, actually. Conceptually, it's very simple. And then for classification, we're going to talk about support vector machines and logistic regression there. And that's really all we're going to focus on too much. In addition, though, as you may have heard just by knowing the various terms of machine learning, there are no shortage of possible machine learning algorithms. There are things like decision trees, boosting, random forests, neural networks, nearest neighbor methods, all these things, and I'm forgetting a lot of them, or just not choosing not to list them, actually, really. And we're not going to go into depth of what those things are and how they work, but we are going to at least describe how they fit into the overall framework that I've laid out so far, and give you some idea, maybe the sort of the basics of these things. And that's going to be this sort of section here. And we're also going to talk about some unsupervised learning algorithms. The majority of what we're talking about here is a category called supervised learning. It really is kind of the predominant, maybe not predominant is the wrong word, but it's kind of one of the more typical ways you see machine learning presented. But I want to at least mention that unsupervised learning methods exist and sort of figure out, or at least describe to you a couple examples in that space. And then finally, I'm going to cover a topic that I think is hugely important. This is all next lecture, but I'm going to cover a topic that I think is hugely important, which is how you evaluate and, more importantly, probably debug machine learning algorithms. Most people, I think, when they see machine learning for the first time, they think that what makes someone an expert in machine learning is knowing a lot of these things. So knowing a lot of different algorithms to try, a lot of different methods you can run, etc. There's the impression that this is what machine learning is. And I think that's actually completely wrong. I think this is what machine learning is. And this is what makes someone an expert in machine learning. So what makes someone an expert in machine learning is not to say, OK, I created my data, built my features, and ran a support vector machine on it. You are not an expert if you can say, OK, it didn't work very well. I didn't get the good performance that I wanted. Let me try a random tree, a random forest right now, and try that instead. And if that doesn't work, you try something else instead, right? That's actually not at all what makes someone an expert. What makes someone an expert in machine learning is knowing exactly what your next step should be. And that includes possibly trying something else. But knowing what your next step should be if you're not getting the performance you want, or to know how that there's just no way you're going to get the performance you want. That really is, in my mind, what makes someone an expert in machine learning. And I think it's hard to become an expert in 2 days of lecture, but I will try my best to make you all at least aware of what makes someone an expert in machine learning. And I should say, I am borrowing a lot of the content here from one of my advisors in machine learning, Andrew Ng, who was, I think, widely considered an expert in machine learning, and also instilled this opinion in me that this is really what makes people experts in machine learning. Okay, but let me start off with just a basic introduction here and talk about what machine learning is. Well, first of all, and don't worry, this is actually not a test here. We are going to have one today. We are going to have one tomorrow again, but I think there's none for today. I'm just reminding everyone that machine learning is what everyone wanted to learn about in this class, apparently. It was the most popular thing here, which is not surprising, right? I think of, there's been a bunch of recent polls in magazines and stuff like that, and they ask what the skills are of, new people fresh into the workplace that employers can't say no to, and machine learning is always the top of those lists, right? It's this sort of buzzword that's very, very topical right now, and it generates a lot of interest, and I think rightly so. It's a really exciting field. I work in machine learning, so I'm very excited about this field, and I hope I can describe to you the way I view what machine learning is. Okay, so let me start this with a little bit of motivation here. And this is motivation, but it's actually also a very concrete problem. This will be your homework problem for next time, by the way. You will do this. So this is not hypothetical. For that reason, it's also not hypothetical because this is actually being done in practice. This is actually being used by the post office, amongst other people, to actually recognize digits. Anyway, here's the problem. You want to take an image of digits like this, and these are real digits. They're written by hand, and these are actually quite clean as far as those things go, right? I can tell what most of these things are myself. Maybe you could convince me that some possibly were others, but I think I can guess what all of these are. The goal is to take digits like this, and this is a very, very famous data set in machine learning. It's called the MNIST data set. Take these digits and tell me what number they represent. So, a little bit more formally, I give you a 28 by 28 grid of pixels. And they can either be maybe 0 or 1. We'll say I think there's intensity because there's some sort of fuzzy edges here. So the pixels have a value between 1 and 256. And there's 28 of these. 28 by 28, 784 of them. And you want to output just a number, an integer that says what that is. Okay, that's the task. This is being done by the US Post Office. That's how they read zip codes. Not to mention a lot of other things, right? I mean, a lot of your phones and such will have handwriting recognition in some app or another that probably uses something like this. So how do you go about doing this? How can we write a program that does this? And as I see it, there are really kind of two ways you could do this. The first way you could do is you could really sit down, think hard about what makes a 9 a 9, and try to encode that. Right? Try to write the logic of a program that will, given an image, maybe you write something that text shapes like this with a little squiggle off the end somehow. I don't even know how you would really do that, but you probably could. I'm sure there is a way to do that. And so you could think about that and write for different digits and think really hard about how different people write sevens. With a line through a 7 sometimes, there's not a line through a 7, etc. And ones can have the base and all these kind of great things about numbers in the US. And you could just try to come up with a program that would do it. Right? This is actually sort of how you write most programs. It's just that the inputs are a little bit more definite, usually. So you could write it like any other program. And people did that for a long time. When AI was first starting, a lot of image recognition was essentially people thinking about the models that they want to fit to this data and trying to build that model, trying to write a program that can kind of fit your image to this model and figure out what's going on. And that, I will just say, and say no more about it, but that is really hard, as you might imagine, right? It's really hard to think about kind of what makes a 9 a 9 and not a 4, because a 4 can look kind of similar, right? Like that could be a 4. And maybe a 4 is more like that usually, but that's kind of like a 9, right? It's really hard. I don't think I'd be very good at it if I had to do that frankly. I don't think I could write a program that would do that very well. So what's an alternative? Well, the alternative approach is we collect a bunch of data. And by that I mean we collect a bunch of images in our desired format. So our desired format is 28 by 28 pixels. We collect a bunch of images that are 28 by 28 pixels, where we see the image itself, we have all the pixels, and we have the actual true digit it represents. That is what this data set is, by the way. This whole data set here has the true labels for what each image here is. And then we try to write a program that is able to tell what the images it's given are. So from the images it's given, it says, okay, this image was given with a 9, and this image here was this pix map, and it said it was a 9. So I want to write a program that if I ever see something similar to that again, and I'm saying similar here in a very fuzzy way because there are lots of ways you can do this, that whatever data I'm given, I sort of learn a model that will fit that data. And given that data, and hopefully more data too, by the way, that's kind of also a key point, which we'll get to in a second. Given that data and really new data, we want to be able to predict what these things, what these images are. And this technique has been wildly successful in a huge number of areas. So as I said, the post office does use this method for classifying their handwritten digits for zip codes. So if you send a letter in the mail, which no one does anymore, apparently. So this is going to soon be a very bad example, actually, unfortunately, and not very impressive. But when you send a letter in the mail and you write your zip code down, it's the computer that scans it. You don't have a person reading every single one of those. Sometimes they make mistakes and the person has to file to sort of correct the mistakes, but typically it's a computer reading it. And this is a paradigm for machine learning. The idea is we don't want to write a program that can do this. We want to write kind of a higher level algorithm that, given a bunch of examples of data, will be able to automatically learn a program that can do the task of interest. Now I should clarify, this is actually a subclass of machine learning called supervised learning. And it's called supervised because we give the algorithm both the image, the pixel image, and the true label that we're trying to predict. There are other classes of machine learning where we just give it the input. We don't tell it what the right answer is, and it has to somehow figure that out. It's a much harder problem in general, but there is a lot of work in that area as well. And so I just want to mention it later in this series of lectures. But I am going to largely focus on, that's the phone in this room ringing. Okay. We'll see who it is. I'm curious now. All right. we will cover this briefly on supervised learning, but I'm largely going to focus on supervised learning. It's a little bit simpler paradigm, and I think things are a little bit more straightforward there. Who was it?
Wrong number.
Oh, it's the wrong number. Oh well.
I just want to make sure it wasn't fire.
All right. So let me jump into that now, and we will get to this problem actually soon in a second. The actual image classification problem, and I said you actually do that for your homework. But I'm going to start off with simpler examples. And this whole class actually is a fairly simple example based not on classification. So classification, remember, we're trying to assign essentially a number of discrete, essentially trying to assign an image a number of discrete labels, namely 0 through 9 in this case. That is a discrete set. I'm going to talk first instead about regression, which is where you want to predict a continuous value thing. So you predict a real number essentially. And it's a little bit simpler to visualize this sometimes, so that's why I typically want to start with it. And it also really, the reality is that, as we will see, the methods we use here for regression translate almost identically into classification. So we're going to use almost the same algorithm in these two cases, with just slight differences. So let's jump into regression. I'm using an example that's dear to my heart. A lot of my research, my own research, focuses on energy systems. And so how do we analyze data from energy systems to make the electrical grid more efficient, to make people better understand their own consumption, etc. This is now a very simple example. This is not my research, but it is a very simple example that I think highlights a lot of good points that really kind of can be the basis for a lot of what we do in machine learning. And I'm going to use this simple question. And that question is, how much power is Pittsburgh going to consume tomorrow at its peak amount? Power actually is a rate of consumption, right? So what's the fastest rate at which we're going to consume electricity tomorrow? Now, this seems a little bit different than the digit problem, but there's actually a lot of similarities here. Namely, I know actually power quite well. I work a lot in power systems. Yet, at the same time, it would be very hard for me to write a program that would somehow just be able to predict, magically, how much power we're going to consume tomorrow. You know, can I add up like all the devices we're going to use? Probably not. That'd be very hard for me to do without any sort of other background knowledge. What I can do, though, is collect a bunch of data from the past about how much power Pittsburgh consumed at the peak of each day, say, and use this data to try to build a model of how much power we're going to consume tomorrow. Now, power consumption depends on a lot of things, certainly. There are a lot of factors that influence power consumption, but one of the biggest factors, not surprisingly, is the high temperature. So what I'm showing here is a bunch of months, and these are not the current month, sadly, as you might imagine. I'm showing high temperature and the corresponding demand, peak demand for that day. This is measured in gigawatts of power, but don't worry the units here. I mean, it doesn't matter, really. This is degrees Fahrenheit, but the units don't really matter. This is temperature, and this is peak power demand. This is very important, by the way, for a system operator that would be scheduling, say, the generators tomorrow, because you have to determine a lot of times very far ahead, you know, how many coal plants you want to turn on tomorrow. If you produce too little energy, you're going to have a blackout. If you produce too much, you're going to be wasting energy. So you want to kind of get a very good guess of how much you're going to need tomorrow to decide what to turn on and what not to turn on. So now I have collected a bunch of data. And this data has high temperature and their peak power demand. Okay, and a big table. And now the question is, if I want to, or not the question, but the fact is, if I want to predict what we're going to do tomorrow, what do? Well, here is a graph now of several days. This is a few more data points. I think about 25 data points. Not very many still, but some. Showing the high temperature on the x-axis and the peak power demand on the y-axis. And what we can do, and this really should sort of remind you, hopefully, of what you did before, what you saw before, when we talked about linear regression and optimization. Because one thing we could do was say, well, there seems to be a relationship here between, you know, the higher temperature is, the more power we use, right? Which makes sense, at least in these months. These are all the summer months, I should add. At least in these months, because, you know, a big consumer of electricity in the summer is air conditioning, right? And so the higher the temperature is, the more power we need in air conditioning to cool everyone down. So I may hypothesize, for example, that the peak demand is going to be approximately equal to some number θ1 times the high temperature plus θ2. This, as we'll see in a second, is just, and you might imagine already, it's just going to be a line in that graph, right? Because that would just be saying we expect to multiply this by some constant and then adds a number, and that becomes our prediction of what we think we're going to consume. And then what I can do is say, okay, well, the forecast, I'm given now a forecast of tomorrow's temperature. Ignoring for a second, that's also a prediction. We'll just assume those are pretty good, actually, weather forecasts. So we'll assume we're given what tomorrow's weather is going to be, the high temperature. then we can predict our likely demand by just plugging it into this model here, right? We plug in the high temperature, and we get an estimate for peak demand. And this really looks like just what we saw in the optimization lecture. This is really just fitting a line through the data. And this line, in some sense, is our model. Right? And all that machine learning is, in some sense, is deciding what that line should be. Right? It is given data, we want to build a model. So given this data, we want to determine what our line should be. OK, that's all machine learning is, right? All right, now let me define things a little bit more formally here. There are a bunch of different ways, and actually, most of this lecture, I should add, does not follow the textbook's presentation of learning. I think that's a slightly older version of it. I have some pointers on the class site to a different book if you want to look at it. It's not required at all. Everything should be in these slides here. But if you are curious, I can also point to some other resources you might see to read more about this. OK, so I'm going to define the following things now. I'm going to define a feature vector, xi, which we're going to assume is always in Rn. Xi represents the ith data point. And notice here that I've made a switch from optimization nomenclature, where x was always the variable we optimized. The reality is this is just the reality of notation in different areas. In machine learning and statistics, x always denotes the input, and y always denotes the output. So we're going to have to just get used to that. So here, we will actually be optimizing over these new variables I'll talk about, which are called theta, whereas x and y will be what's fixed and given to us. So forgive me for that. It's kind of unavoidable when you cover a field that spans so many different areas, like AI does. OK, so we have some input features. And this input feature is a description of what we're providing to our algorithm. So in one case, this could be, for example, a two-dimensional feature vector where the first feature was the high temperature for the day, and the second feature was just the constant term 1. And that seems a little odd that I'm putting 1 in all the things, because that's going to be the same for every single example. We'll see why we do that in a second. And there are actually a few different ways you can formulate this, but I think this is probably the easiest way, at least, to look at things briefly. OK, so this is my feature vector. My output is, for the case of regression, going to be yi, which is just a real valued number. And the fact that it's a real valued number here makes this the regression task. So for example, in our case, the output that we want to predict would be the peak demand of power for the ith day. The next thing we have is a set of model parameters. These are also called weights sometimes. And these things define how we're going to go from our input to make a prediction of what we think the output's going to be. So we have some vector theta, which is actually, in our case, also in Rn. So this is actually the same size here. So the number of features is the same as the number of parameters. That's not always true. But for the cases we'll consider, it is true. So I'll just define them as being the same for now. And finally, we have probably the most important part, which is the hypothesis function. So the hypothesis function, which we're going to write h sub theta of xi, this, or just of x if you don't want to put xi, this is a function that takes as input the features, our input features, and outputs a prediction of the output. So ideally, we want this hypothesis to be close to our output, where close is measured in various ways that I'll talk about shortly. Now, there are virtually an unlimited number of possible hypothesis functions we could talk about. And in fact, when you talk about other machine learning algorithms, a big difference between a lot of them is their form of their hypothesis function. That's the difference. That is what makes a decision tree versus a linear classifier, for example, is the difference in hypothesis function. For this set of lectures, though, we're going to consider almost predominantly what are called linear predictors. Okay, and in that case, h theta of xi, and we write h theta because the hypothesis function, while you can think of it as a function that takes as input xi and outputs something close to yi, it depends on our parameters, of course, right? So it's parameterized by these parameters theta. The hypothesis function we will consider is going to be almost predominantly the linear hypothesis function, which is just equal to theta transpose xi. So you take your features, and that, by the way, is just the sum over all j of the jth parameter times, this is I, times the jth feature. Okay, so you just an inner product between the two things. You take your parameters, take the inner product of that and your features. That is your hypothesis function. That is what we are predicting. There's a question before?
Form of hypothesis function, you mean like this will be one form?
Yes. So this is a form. So this says this is one class of hypothesis functions. It's a very common class, I should add. But this is just one choice. I mean, you could have any function you wanted here, right? You can make it as complex as you wanted. And we will talk a little bit about other possibilities there. But this is basically what we'll use for the most part. This is, by far, I will also say, the most used hypothesis class in a lot of real-world problems. Simple. It might seem too simple, where you can't do anything. But as we'll see in a second, by picking your features to be expressive, you can actually make this an incredibly expressive function here. Okay, so that's our sort of setup to the problem. Does anyone have any questions now? This is going to be, this is going to be kind of the backbone for this entire 2 lectures. So if this doesn't sink in right now, please speak up. All right, moving right ahead. The next thing, and actually like really the last thing that we need to define, is what's called a loss function. So a loss function, remember, I sort of said our goal was to get it, choose parameters such that our hypothesis was almost equal to the outputs. And a loss function is how we measure sort of closeness between our hypothesis and our actual outputs. So, in particular, a loss function, this is a function that takes as inputs 2 real numbers and outputs another real number, and the output actually is always going to be positive, we'll assume. If you make it negative, there's really no point. You're always trying to sort of, loss should always be small, so if you make it negative, then you just sort of, you're talking about negative loss. We just assume loss is always positive. Where, let's see. Okay, I kind of want to bullet these points here. All right, where Ly h theta of xi, this defines the penalty we pay for these 2 things not being the same. Okay? And the simple example here is one we've already actually seen in optimization, which is a squared loss. So we take yi, we take this thing, we take their difference, and we square it. This is nice because it's always positive, first of all, so that's good. And it captures kind of how far apart these two things are, right? It's not the only choice I should add, but it's a reasonable choice. And at this point, we're basically able to formulate almost all machine learning problems. Not quite. There's one element that I'm missing here, but we'll see that in a second. Almost all machine learning problems have a form that's very similar to this, which is called, I'm calling here the canonical supervised learning problem. You can also call it loss minimization. Number of names for it. But the idea here is very simple. We have our hypothesis class. We have a set of inputs. We have m different inputs and m different corresponding outputs. What we want to find is we want to find the set of parameters such that minimize the sum of losses for this hypothesis class. Okay, so for example, actually I think we'll go through an example in a second of least squares. But basically, this is the problem, right? And it's very intuitive. Have some hypothesis depends on some parameters. We want to choose the parameters such that the hypothesis is as close to giving us the data we've seen so far. Right? As I said, virtually all methods have this form, just with different choices of hypothesis and loss function. Plus one additional term, which I'll talk about in a second. All right, so let's talk about least squares now. Least squares, as we saw before, right? We saw it in the optimization problem. You're actually doing it for a homework assignment. This exactly falls into the category of this optimization framework. I'm going to erase this now, but hopefully everyone has this in their minds. I was writing it really just to reinforce it. It's in the slides there. Least squares says we're going to pick as our hypothesis the linear predictor. Our hypothesis is just the inner product of our parameters and feature vector. And by the way, this is also why I should add. This is also why we put a 1 there. It's so that we can have a bias term essentially in our predictor, right? So our model here wasn't just we take this and multiply it by some term. It's we take it, multiply it by some term, and add a constant, right? To give you a slope and an intercept essentially. And that 1 there lets you incorporate the intercept into your parameters here without having to worry about a separate term for it. That's all it's doing. Okay, so we have our linear hypothesis and our squared loss function. Now, what I'll claim is that this is just exactly the least squares problem you've seen before in the homework and in class before. And to do that, well, there's a couple ways of doing it, but really our problem here was just minimize over theta the sum of our losses, which in this case take the form of yi minus, well, our hypothesis function there is just theta times xi squared. That's our problem, which we can also write as x times theta minus y, the 2 norm of this, where we define the big matrix X and the vector Y like this. We take all our features and put them in the rows of X, and we take all our outputs and put them in the rows of Y. We only have one output, so this is a vector. We have many inputs, n different dimensional input, or n dimensional inputs, so this is a matrix. But really, we're just stacking up all the things we have. Now, hopefully, it's obvious to you that this thing here is, in fact, equal to this sum, right? Because this matrix vector product here would say the each element of this vector here would be equal to the ith row of this times this guy. So that would be equal to, the I term there is equal to essentially xi transpose theta, which is exactly this thing here. And then the ith entry there is just yi. The 2 norm of a vector is just equal to the sum of all the elements squared. So these two things are equivalent. Does everyone follow this here? OK. So there, that's our first machine learning algorithm. We've actually already done it. It's just least squares. And really the only important point here is sort of how we defined our hypothesis function and our loss function in order to get to this point. Now, I should also add, this makes our problem essentially, our least squares problem, be minimized over this. Minimize over theta, x theta minus y. And since we already know optimization, we can say a couple things. We can say, first, this is the convex problem, right? This term here is linear in theta. It's the 2 norm, which is a convex, or 2 norm squared, which is a convex function of a term is linear in theta. Therefore, this whole thing is a convex function. We can solve it. You could type it into CVX pi, and it would just solve it. This is also happens to be that one case where you can actually also solve it analytically. So we actually can also write down the derivatives here in their analytic form, set them equal to 0, and get a solution that way. So I'm going to do this sort of very quickly. We talked about gradients a little bit before. It might be a little bit foggy if you had just seen it the first time in that one lecture. So I'm going to go through this, actually in a little bit more detail even than in this slide here. But this least squares problem is one, and really probably one of the only cases where we actually can just immediately get the solution by essentially solving a set of linear equations. OK? So how do we actually solve this thing? I'll erase this here, but it's right up there. OK. So remember, we said that for a convex problem, one way to solve it, if you can do this, is take the gradient. The gradient is the set of derivatives with respect to each element of our vector we're trying to optimize, and set that equal to 0. So we take the gradient with respect to theta of this thing. Now, it might not be obvious at first how to compute this gradient here. And you can do it a few ways. I'm sort of showing you the end result here. But let me sort of show you one way of getting there at least. OK, so the way we can get there is to notice that for a vector x, I probably shouldn't use x. Let me use z. I use x for too many things already in this course. For vector z, the 2 norm of z squared is just equal to z transpose z. It's the inner product of z with itself. All right, so we can actually write this thing a little bit, maybe not more compactly, but a little bit maybe sort of more intuitively, writing it as x theta minus y transpose. So this whole thing equals the gradient theta of this thing times x theta minus y. OK. Now we can sort of just distribute these things out. Remember multiplication, because it distributes over addition. So it will also be equal to the gradient of theta transpose x. Remember, when we transpose a product, we transpose each of its elements times theta minus 2 theta transpose. Actually, I'll write it 2 y transpose x theta plus y transpose y. OK, now actually we can apply some of the rules that we very briefly mentioned in the last slides. When you have some form like this, where you have and then this is the gradient of all these things. When you have something like this, taking the gradient of what's called here a quadratic form, because it has theta appearing on both sides here, just like the derivative, I'll make sure I'm all on the camera here, but it's like the derivative of theta of, say, a theta squared. If theta was a scalar value, that would be equal to 2a theta. The derivative of this whole thing is just equal to this guy here, is equal to 2x transpose x theta. Okay, it's just sort of the analogous rule as you have for the scalar case. This thing becomes this guy here. That would be minus 2x transpose y. This thing does not have a theta at all, and so it just goes away when you take the derivative. And so that's here is the same thing as this, distributed out a little, just distributed out a little bit. Now, to actually find the optimal theta, we set this equal to 0. We want to find the theta for which this is 0. Move this to the other side, multiply by this, and you get theta star equals x transpose x inverse x transpose y. All right, and this actually it's such a common equation. It has a special name. This here is called the normal equations sometimes. So this is the solution, sometimes called the normal equations. And this is sort of the one case where you actually can solve these things exactly, or not exactly, but you can solve them just by plugging it into, into the matrix inverse. And in fact, here's some code that will do it for you in Python. It's actually a lot faster to do in MATLAB, but Python works just as well too. So let's say we have our temperature data in a file, and we have our peak demand in another file. We will just load the first file. This thing here, just make sure that it's actually loaded as a column vector. Don't worry about this. This is just the way of forcing it to actually load as a column vector. And then mat makes it a matrix instead of an array. NumPy, if you're familiar with it, has two designations. It has matrices and arrays. And you want to do all this with matrices rather than with arrays. This here just adds an extra column of 1s to the ends to add that constant term. And then this solves this set of equations here. It solves this inverse times that. It's actually always almost better to call a function like this instead of actually forming the inverse itself and then multiplying it, because that forming of the inverse is actually numerically kind of an unstable operation sometimes. So these sort of solvers are actually the way to do that. Okay, so there's our first machine learning algorithm. It's one line of Python actually, right, after you've loaded everything else. And it's one line of MATLAB. It's actually in MATLAB, or in Octave, it's one character even. But we won't worry about that here. Here we're going to use Python, so it's a few more. All right, are there any questions?
How do you compare the solution with
You mean how do you compare? How do you compare it?
Yeah.
They will be the same to numerical precision. I mean, this is an optimization problem that has a single optimum. They're going to be the same. This one will be a lot faster to solve, just because, I mean, CDX pi is a very general solver, right? You have this huge hammer to wield, and you're basically telling it, you can solve any problem, solve this really simple problem, which I know how to solve myself, but it doesn't know how to solve it. So it'll have to figure it out. It'll go through a much more complex way of solving it, and it'll get the same solution to numerical precision. Okay, so there's our first machine learning method. And by the way, this is the first one. It's also the one that I will actually use first every single time I work with a problem. You never run, the most advanced machine learning algorithm you can think of the first time you have a problem. You see how well linear regression does, and then you go from there only if you need to. All right. Now, one thing that sort of might seem strange is, why did I choose that squared loss function? It's kind of arbitrary, right? Why not absolute loss? Seems a little more intuitive, if anything, right? Rather than like taking the difference and squaring it. And I guess you square it because to be positive, but wouldn't the absolute value be much more natural, right? Why squared? Why not to the fourth or something like that, right? I'm squaring it, yeah.
It's absolute, and if you get further away from the point, you would, and then minimize that equation.
Yes. So actually, that's really a great point. That's what I'll get into in a second. That's sort of why you might want to use one over the other. So they are different, right? Because if you have a loss, so what I'm plotting here is I'm plotting squared loss as a function of the difference between your hypothesis and the actual output, absolute loss, and then also something called deadband loss. So squared loss grows like x, like this thing squared. They're all positive, by the way, but this one grows like this thing squared. This one grows like the absolute value. And so in this range here, this is actually bigger, but in this range here, it's lower than the absolute loss, or than the squared loss. So there's sort of two answers to this question about why you would use squared loss. The real answer, the fake answer is, well, you can come up with probabilistic models that justify why this is the right thing to do, and under certain assumptions, under certain Gaussian assumptions, this is the likelihood of a random variable appearing, and that's all great and that's all true. The real reason why you do it is because you can solve it quickly. I think just that's the fact of the matter, right? Is that it's one line in Python. That's why you do it. Absolute loss, this is still a convex problem, right? It certainly is, but it's not differentiable anymore. You can't take gradients anymore. And the only way you can really solve it is to plug into a solver like CVXPy. There are actually ones that will be faster, because CVXPy is very general, so you could actually plug it into one that's much more specialized. But that's sort of how you do it. That's just what you have to do. And that can be a lot more of a pain than just writing one line of Python code. Now, you may actually want to do that, though. Right? So let's say, so this is still a convex problem. We can still solve it. But why would we want to solve it? And I think, yes, you're getting to that point exactly. The idea with squared loss is that once you start getting away from 0, your penalty starts increasing very quickly, right? Like the square of your distance between your prediction and your true output. That's really fast. The absolute loss grows much slower, right? And so the way to think about this is kind of similar, and it's exactly the same actually, to the median versus the mean in estimators. So if you have a bunch of numbers and take the mean of them, that can be easily influenced by a point. One point is very, very far away. Whereas if you have a bunch of points, take the median, you can take one point, move it very far away, and it won't affect your median at all. This is actually just a generalization of that. If you have no inputs, if your input is just the constant feature vector, these things will produce the mean or the median of the data set respectively. Don't actually think about that. That didn't make sense right then. And when in the case that you have a lot of features, these essentially are analogous to a median-like or mean-like quantity. So the squared loss, if you have one data point that, I'll go back a few slides here, sorry about that. If you have one data point here that's very, very far from this line, the squared loss would be very, very badly affected, or very largely affected, we'll say, by this one point down here. Whereas the absolute loss wouldn't be that affected by it. Okay? That's why you might want to use one over the other. But again, the real reason why you do it is because it's fast. And sort of and they also, a couple things. First of all, they have kind of funny names. So this deadband loss I showed you. This loss here is like absolute loss, but it has this deadband in between 1 and -1, or between some other negative epsilon and epsilon, say. And you basically take this thing, you subtract epsilon, take the max of that, and 0. And if you minimize this, plus another term we're talking about in a second, but really just minimizing this, that's an algorithm called support vector regression. It's a wild name, right? You may have even heard that name before. It's just doing that. It's just minimizing deadband loss, this other loss function, with a linear classifier. It's the same. It sort of feels like the same algorithm almost. All right. The good news maybe good news, is that if the data is sort of nice, and in a lot of cases this is true. So I showed you a case where sort of these two could give very different results, right? If you had one point here that instead of being here was way down here, that would make the mean, or rather the squared loss and the absolute loss estimators very different. Right? Because the squared loss would be very affected by that, the absolute loss would not be affected by that. The kind of good news is that for a lot of data, these things produce estimates that are not that different from each other. It's not a hard and fast rule. The idea being that if you have data that fits one of these models very well, it'll probably fit all of them very well, right? If you have a bunch of points that are really close together, the mean and the median probably are kind of similar. And just like this, there are a lot of cases, not every case, but there are a lot of cases where it doesn't really matter which one you use. You can use whatever you want, and they all work kind of okay. Given that, then, I would like to use the squared loss because it's very fast to compute. But that's all the magic really is there. There are differences, and for some data, those differences can be very important. So sometimes they don't always have to be important. OK, were there any questions here? Because we're going, this is kind of fast, but it isn't, hopefully not too complex yet. Yeah?
Okay, and is it because you want to have some sort of tolerance?
Yeah, the idea is sort of, intuitively, I guess the idea there would be, if I'm within some number epsilon of my peak demand, say, it doesn't matter. I don't care. I'm going to schedule, the same amount of power regardless if I'm in some certain band. So I don't really penalize myself for being within, 0.1 or here within 1, but epsilon, that dead band could be whatever size you choose. And it would create different estimators for different sizes of dead band, by the way. So intuitively, it just says within a certain range, I don't care. I'm going to say that I have doing as well as I can. And it's only outside that range that I'm really going to penalize myself. Mm-hmm.
You just use one input to set up like empirical temperature. So are there any other factors? There are more inputs in?
Well, so there's one input, but really, remember, we're mapping everything through the hypothesis function. So our input vector itself is actually can be quite big. So our input vector here was two-dimensional. It had the constant term as well as the temperature. We'll see in a second how it can be much bigger. For the case of images, our input vector would be 784 dimensional. But the loss, if you do a regression loss at least, which wouldn't be quite right for the digits, but forget that for now, the loss is still a function of these two scalar values, though. Because our output is scalar valued, right? That's what we're trying to predict. And so our hypothesis is also going to return a scalar value. And so what we really want to do is compare those two scalar values. And there's no real point in having a higher dimensional loss than that. The other thing is you can't minimize. It's very hard to minimize, a 2D function. You have to pick something you prefer to minimize over another, right? You can't minimize a vector. You can only minimize a function that outputs a single scalar value. So we're going to always assume that loss takes two scalars as inputs and produces a scalar value. All right. Moving right along. So we're going to talk now about a couple things. The first being what I'm putting in quotes here as nonlinear regression. And the idea is that it might seem as though this linear set of predictors is very limited, right? Linear predictors seem fairly limited because they seem like they're kind of restricted to fitting lines through data, and lines seem pretty limited in what they can actually categorize. What if our data is not on a line, as it often may not be? I don't know if any lines really capture like what images do for digits. Is that the case or not? So these might seem limited, but they're actually quite powerful because we can choose as input features really anything we want. We're not limited to just sort of single inputs or single inputs of kind of the true underlying input we care about. We could also, for example, put the high temperature for the day squared into our set of input features, along with the high temperature, along with 1. Or to the third or the fourth, or whatever power we want. And in this case, this linear hypothesis here will really be a nonlinear function of the kind of, in some sense, the original data, right? So if we think of just the high temperature as being our original input, then when we form this feature vector here and take a linear hypothesis, that's actually going to be a polynomial in this high temperature. Right? It's still linear in the parameters, but now it's producing kind of a nonlinear prediction in the temperature itself. Importantly, though, because the actual form of theta doesn't change at all, and theta is what we're solving for, remember, this doesn't change anything in terms of the way we solve it. So we still have the exact same solution, theta equals x transpose x inverse x transpose theta. Or for the absolute loss or anything else, it's still the exact same problem. You just have a different dimension feature vector and a different dimension set of parameters. And this is really where these methods derive their power from. They're actually incredibly powerful because you can put whatever you want into your input feature. Let's take a look at what this looks like then. So now I'm going to go beyond just those summer months that we all wish we were in right now and talk about the current reality, which is that it's not as if you keep having lower temperatures and power just keeps going down and down. At some point you bottom out, and maybe if it's the high temperature 20, it actually comes back a little bit because now people are running electric heaters instead of air conditioners. Well, I actually don't need to erase this quite yet. So what are we going to do here? So this is now about 50 days in Pittsburgh, showing high temperature versus peak hourly demand. Well, now a line is not a very good fit through it, right? A line, if we just draw a line kind of like this, it doesn't really capture what we want to capture. What might be better is to use an input feature that actually has a second degree polynomial. So it actually has both the high temperature squared in the feature vector. Or maybe we're going to go to the fourth power polynomial. So that's high temperature squared, cubed, and to the fourth. When I say the polynomial here, I mean that we actually have a term for each different power, from the constant term 0 to the linear term 1, quadratic, cubic, etc. Okay? So here there were, for example, actually how many parameters would there be here? In a fourth order polynomial, what size? Right. So theta here would be 5-dimensional, because 4 for each of the polynomial terms and 1 for the 0th term. Okay, so this is looking good, right? I just didn't plot the line. The line would look really bad. It would look kind of like this, which wouldn't capture any of the fact that we do. In fact, increase back up there. It looks pretty good. We're getting seems to look pretty good there. Let's just keep going. Keep going higher and higher orders. Something weird happens here. Now I'm going to show you a 30-degree polynomial fit to this data. Okay? And I do not think that's a very good model for what peak demand does based upon temperature, right? But the weird thing here is that according to the actual error, so according to this actual metric, the sum from I equals 1 to m of yi minus h theta of xi squared. According to that, this is really good. And you can see it too, because it's actually passing exactly to these data points, right? So it's getting them exactly right in some sense. And this is actually getting at one of the central issues in machine learning, which is essentially training error versus what's called generalization error. Okay, so the idea here is that we are optimizing, we are finding parameters theta that minimize this loss, right? And this loss evaluates our loss on our m data points that we have, our m examples we have, sometimes also called the training set. But what we really care about is how well this hypothesis could predict a new example. So I'll give you a new day, whatever that may be, right? So this is sort of a fuzzy concept, but I somehow get a new day, and I want to predict what the peak demand is going to be. That's what we care about, right? Not just recreating our old data. It doesn't really matter if we can perfectly recreate our old data. We have the data. What we care about is making a new prediction. This is called generalization error or generalization loss. And so a common way, now it's kind of hard to do this exactly, right? Because there, in some sense, you know, if we knew every possible future example, we could just also map every possible future example and come up with a program that worked perfectly every time. But we want some way of knowing, like, what's a typical new thing going to look like? And so one common way of doing this is to take our data and divide it into two different sets. And I'm going to call one set of these the training set, and one set a validation set. Now, if you've heard this before, I'm not using the word testing set here, because that actually is a little different. So bear with me. I'm calling these training set and validation sets. In general, what we're going to do is the following. We're going to use the training set to solve this problem. So this problem, or sorry, this problem, minimize over theta of the sum of all our losses. Well, this is the squared loss, but in general, it would be the loss of these things. Okay, we're going to minimize over theta of the sum of all our losses. That's what we use the training set for, to find the parameters that minimize our loss, sum of losses. We're going to use the validation set to actually choose our hypothesis class in the first place. Okay? Because remember, we can choose this to be whatever we want. And I'm a little bit abusing notation here, because I'm actually saying the hypothesis class also sort of implies how many, for example, how many features we have, which, you know, maybe that would be defined by your input, you would say, but hypothesis class really can, you can define everything, so the hypothesis class actually, you know, defines how many, what degree your polynomial is, etc. So I'm going to wrap things like the degree of the polynomial, the number of features we have. I'm going to call that all kind of part of our hypothesis class, right? And we're going to then use the validation set to pick which hypothesis class we actually want to use. So we can have many choices, right? We can have the choice of a degree 1 polynomial, degree 2, degree 5, degree 40. We're going to let the validation set determine that, and then for each model hypothesis class, we're going to fit the optimal one by training on the training set. And this, hopefully, and we'll talk about sort of the pitfalls of this in a little bit when we talk about evaluating machine learning algorithms, but hopefully this will actually give us a good estimate of sort of what this will actually look like on new examples. So we can see that. What I'm going to plot here now is the training set in blue and some other examples in green. And in green, we're not going to use it to train to pick our parameters. We're just going to use it essentially to evaluate how well the thing is doing in general. So here is a fourth order polynomial, and I'll get actually plots in a second of the error, but it looks pretty good. And you can actually imagine this sort of a reason why you think this is good is that it looks like a good estimate both for the training data and for the validation data. This one, on the other hand, fits the training data very, very well. But even small places, like right here, right? That's just a huge error right there on that one point, because it's not actually trying to fit, doesn't even know about examples in the validation set. So the figure to have in mind here is the following. And this is actually a really important figure when it comes to machine learning. On the y-axis here is loss, measured somehow by whatever loss function you have. And the x-axis is some notion of model complexity. So this could be degree of the polynomial. It could be, there are lots of other ones I haven't introduced yet. We'll talk about a few in a second. The typical situation here is that at the beginning, when you have a really, really uncomplex model, the error, the loss on the training set and the validation set are both high. Right? Because it's a bad model. You can't fit anything with that. As you increase complexity, the loss on the training set will always decrease, right? Because a more complex model, if you're actually able to optimize this, the more parameters you have, the better you will always do. You will never do worse by adding another degree to your polynomial on the training set, right? Just have a more expensive function. What will happen, though, is that after a certain point, you will start to have your error increase on the validation set. You start performing worse kind of on the true generalization error that you really care about, or at least a surrogate for that. And we would like to choose our hypothesis class to be somewhere kind of in this sweet spot here, right when the validation error is the lowest. So here now is actually a plot of the loss versus the degree of the polynomial. And importantly, this is actually on a log scale. So these are very big losses very quickly. If I showed it on a non-loss scale or a non-log scale, you wouldn't even be able to see anything but a straight line down here. And it kind of confirms what you see visually, right? So at first, sort of goes down. Things look okay. The training set loss just keeps getting lower and lower, which is great. The validation set, a little higher at first. Maybe that's understandable because you're not sort of directly minimizing that one. But it keeps going down for a while. It does bump around some. This is not a monotonic or even a smooth function necessarily. But then once after a certain point, after a fifth degree polynomial, you just start getting bigger and bigger losses that just don't really help. So you're essentially overfitting to this training set. And you are not fitting the true data very well. Now, the last thing I'll say today is that there are a few different ways you can control this notion of model complexity. Okay? The one that I described so far was the sort of the intuitive one. It is basically how many features do you have? That's an obvious notion of complexity, right? Because the more features you add, the more complex your model is, the more it can describe. A less obvious one, but which is hugely important and really makes sort of the canonical machine learning problem, is we can control the complexity of the model by keeping the magnitude of the parameters small. This is not obvious at first why this is the case, but it is the case. So let me try to sort of illustrate why this is. Let's take this function here. The way this is a 30th order polynomial that manages to pass through these points exactly. Okay, not close, because if it was close, you miss by a little bit here, and you're way far. You have a really high loss. It hits them exactly. And the way it does that is it picks really big values for those parameters. So they're like in the 10 to the 10 range, these values. And it has one that's really high and one that's really low, and they cancel out perfectly at this one spot to exactly go to that point. And the same thing there. I mean, you have to have a bunch of things, otherwise other things cancel out exactly to hit that one there, and so on. So the way you've accomplished this is by picking really high weights for your parameters. Really large weight. I mean, by high, I mean either high in magnitude. So either really big positive or really big negative. And that's the only way you can get a function that looks like this, is by picking really big weights. So an obvious thing we can do is take our objective and directly penalize some measure of the size of the parameters. And an obvious one would be just the 2 norm of theta. Right? That will be big if this has big entries. It will be small if it has small entries. And instead of just minimizing just the loss, we're going to minimize actually a weighted combination of this L2 norm of our parameters and the sum of the losses. Where lambda here is what's called a regularization parameter, And that's just a positive number that essentially trades off the relative importance between this term and that term. Now, one of the things that's very nice is that in the case that you have squared loss, this is also a nice differentiable term, quadratic term. And you can actually solve this thing. So you can actually solve the case of of least squares loss plus regularization analytically as well. The solution ends up being very similar. You just basically take this thing and you add the identity times lambda in this product here. I won't go to this derivation, but it's exactly the same as the one I had on the board before. This extra term just pops out because of the gradient of this term here. Okay, so this actually, I should say, this is the real canonical machine learning problem. A huge number of machine learning algorithms solve this problem. That's all they're doing, is solving a problem like this. So let's take a look at what this looks like. So here now is a plot of training error and validation error for different values of lambda. And importantly, lambda here I'm showing on a log scale. So lambda, you should always think of lambda scaled like logs, because the difference between 1 and 2 or 1 and 0.1 is not going to make that, or 1 and 1.1 is not going to make that much of a difference. Lambda really, just because the actual problems themselves are weighted differently sometimes, you typically will want to choose a range of lambdas on a log scale rather than on a linear scale. This is a plot now of the log of lambda, or rather a plot of lambda on a log scale versus training and validation loss. One thing to keep in mind is that here, big lambda means we are penalizing this very heavily. That means we're going to have lambda or theta be very close to 0, right? Because we're essentially saying we're going to pay a big cost for having this be very far away from 0. So our actual value will be very, very close to 0. And so here we actually get the flipped version of the opposite chart, where this is the side where we have very low model complexity. Here, this is the least squares solution. Here we're not penalizing lambda to within numerical precision at all. And so we're going to get the same thing as the least squares solution here. So we have low training error. That's great. We passed all those points exactly, but really high validation error. And the sweet spot lies somewhere in the middle. Importantly, not at all a smooth function. It can jump up and down a lot. This is the one I showed you on the actually, sorry, I'm going to show you on the next slide. If I take this point right here, that's actually almost exactly at 1. Here's the function. Here's now the 30-degree polynomial with regularization. So it looks nothing like a 30-degree polynomial, but without regularization, it looks like a very reasonable approximation to the function we care about, at least on this interval. Outside the interval, sort of everything is up for grabs. But on this interval, it looks pretty good. And as I said, this really is kind of what, not all, but probably maybe half machine learning algorithms there are, will be something like this form. You minimize a sum of losses plus some regularization on your parameters. If you're lucky, this is a convex problem, so we can use convex methods. And in fact, all the ones we've seen so far are convex problems, so we can use convex methods to solve it. If you're unlucky, you can't do that. But this is really what we solve. That goes for regression and classification, I should add. So next time, we're going to talk about how you formulate classification problems in this exact same framework. It ends up being a very, very small change you have to make. And then the exact same thing applies. The last thing I'll say is, we chose the L2 norm here somewhat randomly, right? Just like we chose the squared loss randomly. And much like the squared loss, the reason we're choosing L2 there is because it's easy. It's smooth. We know how to optimize it. But there are other choices, and other choices actually can have very good reasons to use them. So a very common another choice of measuring the size of theta is to use the L1 norm. The L1 norm is a sum of absolute values of the elements of theta. And there are a bunch of reasons for this, but one of them is that this actually, for technical reasons, will actually cause a lot of the values in the solution to be exactly equal to 0, which can help you out in figuring sort of what are the important and relevant items. What are the relevant features that you actually sort of are using to make your prediction? So that is it for today. Tomorrow, and I don't have any more slides, so that's good. But on Wednesday, we will talk about how to extend this to the case of classification when you want to actually categorize discrete things rather than continuous things. All right?